Hello, everybody. Welcome back to Markov processes. How is the homework going? I think we should talk about one, but I don't want to make you sit through it. I didn't think it was going to be as tricky as it turned out to be. So let's do it. Okay, so one on the homework is, oh, I'm not sharing. We have an MM1 queue with 0 customers. And we want the expected amount of time it takes for the system to first hit 2 customers. I thought we might be able to do this as some kind of maybe negative binomial kind of thing, which is a generalization of the geometric, which counts a number of trials until not just the first success, but like a 4th success. And if we could count those up, we'd have to figure out how many of them were services completed and how many were times to arrival. And we would have to adjust that by 2 different exponentials. But I don't know, that's too hard, I think. So maybe you had a better idea, but here is my idea. So I've got an MM1, and so this is a number of customers, and we're starting with 0, and we go up and down and up, and maybe down once more and up and up. So here is the first time that we hit state 2 in this picture. This is state 1 and state 2. And so here is my hint for you. So if I want to do this like a first step analysis, and if you let TI be the first time starting from I to hit state I plus 1, then what we want to find is the expected value of, so starting from 0, we have to go through 1 before we hit state 2. So we want the expected value of T0 plus T1. The expected amount of time, this is an exponential time, this is a continuous time, to go from state 0 to state 1. And then starting at 1, how long does it take us to first hit state 2? But as you can see in this picture, that may involve us going back to 0 several times. But if you do a first step analysis, you can handle this pretty well. So of course you can run that expectation across, and starting from 0, the expected time it takes us to first hit state 1, this is this time right here. This is an exponential amount of time with rate lambda. That's the input process, the Poisson process. So this is going to be 1 over lambda. But the expected amount of time starting from 1 to hit state 2, a first step analysis here would be to say that this is the expected time starting from 1 to hit state 2, given the first move is up, from 1 to 2, times the probability the first move is up, and then the other term, plus the expected time it takes to go from 1 to 2, given the first move is down, in which case we're kind of going to sort of be starting over at time 0. So the first move is down times the probability the first move is down. The first move being up and down, those probabilities, think bug racing, think superposition and thinning. If you look at every event in the process as being from a Poisson process with rate lambda plus mu, so if there's at least one person in there, the next event is either an arrival after an exponential amount of time with rate lambda or a departure after an exponential amount of time with rate mu. So the time until the next thing, the transition, is exponential with rate lambda plus mu. You get that from the minimum of those 2 exponentials. And the probability that you go up is the relative rate of going up versus the rate of that exponential time until the next transition. Going down, this is going to be the rate mu over lambda plus mu. So we talked about that a lot back when we talked about bugs racing. Okay, so we need these other these other expectations. If the first move is up, then we will have hit state 2. And so how much time did that take? The expected time starting from 1 to hit state 2, given the first move is up. This is just the expected time to a transition. We already know it's up, so we just need to know when the transition's occurring. And because the time of the next transition is the minimum of an exponential with rate lambda and rate mu, it is exponential with rate lambda plus mu. So the time to a transition is exponential with rate lambda plus mu. So this is 1 over lambda plus mu. Please let me know if you had a slicker way to do this. But I've got one more piece here. The expected value of T1 given the first move is down. So I'm at state 1 and I want to know the expected time to hit state 2, and the first move is down, so it's not happening. I'm going down to 0. So first I have to wait that out. So I'm going to have 1 over lambda plus mu. That's the expected amount of time for that first move to hit 0. And then I have to start over counting the expected time starting from 0 and add the expected time starting from 1 to go up by 1. So let me separate those. So expected value of T0 plus the expected value of T1. And you have everything. We know the expected value of T0. It is the 1 over lambda that's near the top left of your screen. And then we're trying to find the expected value of T1. You are going to end up with an expected value of T1 in here, but you could solve for it. You can move it. You can isolate it. So most of the rest of this, with I guess the exception of 3, are fairly short problems if you want to use the formulas we've derived, and by all means use them. So in 2, we have an MG1Q. So this is exponential inter-arrival times with some rate lambda and then a server, and the service rate is assumed to be mu, but if S is a service time, it's no longer exponential. It is gamma alpha beta. So you can go look up the mean and variance for this, but if you're using the gamma alpha beta, if you defined it the way I define it, because some people have 1 over beta or I have a beta, the expected value of S is alpha over beta. And we're going to need, not for A, but for B, the variance for S. And in my parameterization of the gamma, it's alpha over beta squared. So, but yeah, so that's the setup for B actually. No, we need that as well for A. Mu everywhere in statistics is a mean or an expectation, but in queuing, it's a rate. So mu is 1 over the expected service time. This is like the only time you'll see something like that, because mu is always an expectation or mean in statistics, but it's 1 over. It's supposed to be the rate. So let me put that in there. Here, it's the service rate. So we have that this is beta over alpha. So for part A, we want the probability that an incoming customer has to wait for service, and the probability that the incoming customer will have to wait. This is technically using pasta, but you don't need to say that. The arriving customer sees the pre-jump chain sees the system in equilibrium. And if you discretize the process that way by just looking at what the arriving customers see, then you will not mess up the stationary distribution. But this is the probability that there's greater than 0 customers there when they arrive. And this is just 1 minus the probability there are 0 customers. And I did state in class, we didn't show it. We talked about how you might show it using busy and idle periods, but showing it by solving the stationary equation is very hard. It looks the same as the MM1, even though this is an MG1. The other probabilities like pi1, pi2 definitely do not look the same. And we have mu, so we can write this answer in terms of lambda, alpha, and beta. And for part B, you should use the formula we derived. So L was the expected Q length of the chain. This is not Little's law, but just like Little's law, it's the same kind of notation I hate, because I would put an expectation on that L, but this is already an expected value. And we derive this to be the expected value of n squared. Now, n was the number of arrivals during a typical service period, plus lambda over mu minus 2 lambda over mu squared over 2, 1 minus lambda over mu. And it still doesn't appear that we need a variance, but we computed the expected value of n squared, and that's the number of arrivals during a service period. And the number of arrivals during a fixed period is a Poisson, and we conditioned on the time of the service. And this turned out to be lambda over mu plus lambda squared, sigma squared plus 1 over mu squared. And sigma squared here is the variance of the service time distribution. So this problem is really just plugging it in, and no, you don't have to simplify it. So really you don't even have to plug it in. If you state this and you write down next to it a bunch of bullets like mu is this, and as long as you define everything in there, that's good enough, because it definitely doesn't simplify to anything nice. Okay, so I don't know if you guys have questions about the other one I thought we should look at anyway is 3. Just to remind you, we do have a formula here as well. So if pi I is the stationary distribution for the continuous time Markov chain, in this case in MM1Q, we know this is 1 minus lambda over mu to the I, as I goes from 0 on up. And we look at the event embedded process. So every time something changes, and you might think that that is covered by pasta, but it's not. So this is the number of customers. If you're looking at the pre-jump chain as covered by pasta, you're looking right here. So you would have an x0 equals 0 and an x1 equals 0. And you're looking right here. So you would have x2 equals 1. And you're looking like right here if you're doing pasta in the forward direction. So the third time someone arrives and looks at the number of people in front of them, there is 1 person in the system, because when this person arrives, they increase it to 2. And we can look at this with the little yellow dots just after a departure, but what we're doing is actually looking at it at every single change. So we're starting at 0, and then the next time this thing changes is it goes to 1, and the next time it changes, it goes to 2, and the next time it changes, it goes down to 1. And if we let pi I tilde be the stationary distribution of this time embedded chain, the so-called jump chain, then we showed in class, and you can just use this, you don't have to rederive it. So we showed that the 2 stationary distributions are related like this, that pi I tilde is proportional to pi I times VI. And VI is the negative of the diagonal entry, which are already negative, so VI is positive, of Q for the continuous time chain, the MM1. We don't have a Q for discrete time chains. Q says if you're at 0, you will move to 1 with rate lambda, and you cannot move more than that in 1 step. So the diagonal entry at 0, 0 is lambda. Starting at 1, you'll move to 2 with rate lambda, and you'll drop down to 0 with rate mu, and the diagonal entry is the negative of lambda plus mu, and that just stays that sort of tri-diagonal thing after row 0. So V0 is the negative of Q0, 0, which is positive lambda, and VI is positive lambda plus mu for I equals 1, 2 on up. So you want to find this distribution. We know this geometric distribution, we have these, and if you multiply those things, you will not necessarily have probabilities. And even if you did, they will probably not sum to 1, and that's what this proportional thing is for. So write down an expression for pi I tilde for all I equals 0 on up, and then sum those and set it equal to 1 to find the constant that you need to divide by to make it all so that it actually sums to 1. Okay, so I guess I am gonna move on. We were talking about bulking. I don't have that much more to say about it because it's not nice. And we were just talking about an MM1. And bulking is when someone arrives and they're like, no, I'm not getting on that line. So I just wanted to recap though, and say that our first case was arriving customers join the system with some probability P. And that's not really making much of a decision. All that's doing is thinning out the arrival process. So we're going from a Poisson process with some rate lambda to a Poisson process with some rate P times lambda. And the mu exponential service time rate mu is still the same. And so we know that the long run probability of there being n people in the system is just the geometric, but our lambda has been replaced with P times lambda. And this is for n equals 0, 1, 2 on up. And for anything else, I think we did second, we said, okay, they're going to join if there's no one there. But if someone is there, then they will join with probability P. So the second case we had is if a customer is arriving, if no one in the system, when a customer arrives, definitely join, go right into service. Otherwise, join with probability P. That's only slightly more realistic. And I think we got through this last time. I think it's the last thing we got through. So we just started over as a birth and death process. Lambda 0 is lambda, the arrival rate, and lambda I, if I equals 1, 2 on up, we're then thinning the arrival rate. And if you use the formula, lambda 0, lambda 1 through lambda n minus 1 over mu 1, mu 2 through mu n pi 0. I'm not sure if we finished it, but I think we did. We got mu minus lambda p over mu plus lambda 1 minus p times p to the n minus 1 lambda over mu to the n. And that held for n equals 1, 2 on up. This formula actually doesn't hold when n is 0. If you plug in n equals 0, we found our pi 0, and that was that coefficient, the mu minus lambda p over mu plus lambda 1 minus p. So I don't want to redo that whole thing because I think we did it. But the third one is where it gets interesting and also almost impossible to solve, which is why simulation is important, even for simple models. So the third one is going to be that the arriving customer takes a look at the system and how many people are there, and they make a decision to join the queue with some probability that is probably decreasing in the number of customers that they're seeing. So arriving customers seeing n people in the system will join with some probability Pn, like maybe 1/2 to the n. But even nice Pn's, like 1/2 to the n, they're hard to find the normalizing constant. So yeah, you would approach it as a birth and death process. You would say that lambda I, the birth rate when there's I in the system, is going to be the Poisson rate, lambda, times pi. So you're kind of thinning it out as you go. You know, you're changing the rate of arrival as you go. And then the mu I is going to be mu, that's always the death rate if I equals 1, 2 on up. And it's going to be 0 if I equals 0. So then you use the fact that pi n is lambda naught through lambda n minus 1 over mu 1 through mu n pi 0. And when you put this stuff in, you will get n of these lambdas and you will get n of these mu's. So you will end up with lambda over n, lambda over mu to the n. But in the numerator, you're going to get a p0 up through a pn minus 1 all multiplied. So you'll get a product as I goes from 0 to n minus 1 of pi, and then pi 0. Which is okay, but this is very hard to deal with. And I can deal with it for certain nice sequences of p's, the probability you join. But usually when you can compute that in closed form, you then can't sum what's left to solve for pi 0. But the idea is the same. If you can do it, then you do it. So we're just changing the input rate or the birth rates. I was going to do an example where I had my Pn be 1/2 to the n, and I could work out this product for you, but then I can't work out the remaining sums, so you're kind of stuck there. But if you wanted to simulate from this and try to find these probabilities through simulation, we have a couple of algorithms now where you don't need the constant of proportionality. If you don't have this, you can still simulate from it and estimate those probabilities. So there. All right, let's do something that we can handle. And that is, I'm not going to call this 4, but it's sort of in here. It's not balking, but it is the MM1Q with feedback. So in this case, people get through their service and they might have to get back in line. So we have some Poisson process with rate lambda. We have a single server with exponential service times with rate mu. And then when people leave, like with probability P, departing customers rejoin the line. And then with probability 1 minus P, they exit the system forever. So here's a little feedback loop. So for the MM1, we showed that the departure process is actually a Poisson process with rate lambda. So the rate of departure when there's currently 5 people in the system, that rate is mu because the next departure is after the next service, and that's an exponential amount of time with rate mu. But if you're not talking about a fixed number like 5 people in the system, the rate of departure overall is averaged out over, how many people are in there. And we actually showed part of the claim that the departure process for the MM1Q is a Poisson process with rate lambda. So recall that the departure process for the regular non-feedback MM1 is a Poisson process with rate lambda. So if you feed them back in, can we think of this as like a lambda plus P times lambda mu? Like, is that how it's acting? And the problem is that if you have this as your arrival rate, then by the same way we showed part of this claim that the departure process is a Poisson with rate lambda, now the departure process is going to be a Poisson with this rate, and that's got to come around again. So it's not right to treat this feedback as just a straight up MM1 with an adjusted arrival rate, because it's just not, because now the departure process is another lambda plus P lambda. So that really needs to be added back here. So what can we do? We don't know what to do with this. All right, so we're going to talk about our first networks of queues today, specifically something known as a Jackson network. And then I'm going to come back to this and we'll solve this. So let's talk about Jackson networks. Oops. Yeah, I think yeah. To adjust at infinite time. I meant to try that before class. I've never tried that. I think it should work. I'm going to try that and I'll make an announcement after class. I think it should work to have like an infinite sum for your arrival process, but I've got something easier. Maybe. So Jackson networks, our first queuing network, our only queuing network. We're not going to spend that much time in here on other queuing networks. Here you have some number of servers. I'm going to say capital M servers. You have an external Poisson process with rate lambda arriving to the system into the system. The servers might have different service rates, and they are in the basic Jackson network. The rate of service at server I is exponential with some rate mu sub I. Lots of things are independent. So the arrival rate is independent of what's going on with the service rates. The servers are not speeding up because there's too many people in the system, just our normal sort of assumptions about independence. And also part of a Jackson network is we have routing probabilities. So people move between the servers. So Pij we're going to use to denote the probability someone leaving station or server I moves to server J. Do I have to write that? I want to say that. Pij is the probability if you finish at server I, you move to J. And if I or J equals 0, then that is usually used to represent the arrival from the outside or departure to the outside. Let me draw a picture. So I'm going to draw a picture with M equals 3. Here's a server, here's a server, here's a server. We've got an external Poisson process with rate lambda. And in a regular Jackson network, they do not line up back here. They actually go directly to the server that they need to go to. And so we're going to have people maybe, you know what? I'm going to change this up. Go this way. It doesn't matter, but I have another example building off this later where I had it in this direction. So I'm going to call this server 1 up here and server 2 and 3. And rather than write that, I'm just going to put their service rates in there. So mu1, mu2, mu3, service rate mu3 is at server 3. I just don't want to mess it up with extra notation in there. So people come in from outside and they go to service and they line up at the different queues. So there's no like one big line back here. That's not a Jackson network. And when computing the stationary distribution, it's going to be a joint distribution of like a pi n1, n2, n3, and ni is the number of customers at station I. And this includes the person in service at station I. And routing probabilities. So for this particular example, people coming in from outside, maybe they join station 1 or station 2. No one can go directly to station 3 in my example. And they go to station 1 with some probability P from the outside 0 to 1. And they go to station 2 with some probability P 0 2. So 0 meaning outside the system. And that may be a little misleading because on the arrows, I usually have rates, and these are not rates. These are probabilities. But we do know what the rate is because we know that the people that are moving up to from the outside to server 1 is a thinned Poisson process with rate lambda times P01. But this notation is a probability on the arrow, not a rate. And maybe people who finish service at server 1 leave with some probability. They leave forever. And I'm going to call this probability P10. And some of them come back around and get in line here, and that would be probability P12. And then at station 2, they go to station 3, and those people definitely leave. So maybe this is my system. That's a beautiful diagram. Okay, so let me know if it doesn't make sense. So we have something known as Jackson's theorem to give the stationary distribution for this. And Jackson's theorem was originally derived using Kolmogorov forward or backward equations. I don't know which one, but they used the Kolmogorov differential equations. And so I'm going to just state it. I think it's hard to derive because of the dimension of pi. It's straightforward yet extremely tedious to verify that it works using pi times q equals 0, because a Q matrix would have like triples everywhere. You know, it gets ugly, but if you really had the patience to sit down and write out a Q matrix, you could take the pi that I'm about to give you and verify that it does solve pi times q equals 0. So regular stuff, but kind of tedious. Okay, so before Jackson's theorem, we need to solve what are known as flow balance equations. Just like we saw with the MM1, if the arrival from outside is a Poisson process with rate lambda, we saw that the departure process was a Poisson process with rate lambda. And if a Q is in equilibrium, you get this flow in equals flow out for every station. And so I'm going to let, what should I call this? All right, this is the typical notation. Lambda I, this is not a birth rate. This is not a rate of increase when there's I in the population. What does that even mean here? We've got sort of 3 populations. I'm going to let lambda I be the rate into and out of in equilibrium. They need to balance. Station I. So let's find these lambdas because Jackson's theorem is going to be in terms of well, I'll write it. So Jackson's theorem says that pi n1 through nm is going to be a product of individual MM1Qs. And we're going to have a product as I goes from 1 to m of 1 minus lambda I over mu I, and then lambda I over mu I to the ni. They're acting kind of independently. The way you can show for an MM1 that the departure process is actually independent of the number of people in the system, which is wild and does not feel at all intuitive, I think. But you can do it with a reversibility argument. You can just think of the departures as arrivals, and it's really, there's no reason that it would be any different than you thinking of arrivals as departures and vice versa. I don't think it's intuitive at all, but there actually is dependence in here because it comes in the lambdas. So we need to solve for those rates, and then Jackson's theorem will give us the final answer here. So let's solve the flow balance equations. Of course, I don't have the picture in front of me anymore. The rate into server 1 is equal to the rate into the system thinned out or multiplied by P01. This is lambda times P01. And then that is it. That is the only arrow going in to server 1. But server 2, we got some feedbacky kind of stuff going on. So the rate into server 2 or out of, whichever is convenient for you to think about it, in equilibrium, they should be the same, is going to be the external rate thinned down by this probability P02 plus this line right here. So people coming out of server 1, and they're coming out with rate lambda 1. We don't know what that is yet, but that's our rate in or out of server 1. So people are going in here with rate lambda 1 and coming out with rate lambda 1 if we're in equilibrium, and then a proportion, this probability P12 of that rate is going to move to server 2. So what we get is, get this color back, lambda 1 P12. So let me try to write this generically. The rate into or out of station J can be written as the sum of the rate into or out of station I times the probability to go from I to J, and I can go from 0 to M. Okay, so the rate in to station 3 is the rate out of station 2. This, whoa. This arrow right here, the probability we traverse that arrow if we went through station 2, this P23 is 1. That's the only way you go from station 2. And so the rate into station 3 is the rate out of station 2 times the probability you go from 2 to 3. But this is lambda 2 times 1. So this is lambda 2. Lambda J is the rate into and out of station J. And you just figure out like what goes to J. So you can make this sum over all stations, including the outside. When I is 0, we're talking about coming from outside. And take the rate coming out of each station times the probability you move from that station to J, summing over all stations. Usually you then solve this system of equations, and yeah, lambda 1 is solved for. So lambda 1 is lambda P01, those are supposedly known parameters. Lambda 2 is lambda P02 plus lambda P01 times P12. I just plugged in lambda 1. And lambda 3 is the same thing. Okay, so Jackson's theorem says that the probability of seeing exactly N1, N2, and N3 customers, if you look at the different stations, this is going to be 1 minus lambda 1 over mu 1 to the N, oops, not to the N1, times lambda 1 over mu 1 to the N1. And we just have to multiply these together with the second Q or station times the last one. And if it looks weird to you that they look like they're all independent, remember that there is kind of a dependence built into those lambdas. And this is going to be N1, N2, N3 have to be some non-negative integers. Okay, so obviously I didn't derive this. I said we can verify it with pi q equals 0, and it's incredibly tedious. But do the mechanics make sense of how you would find such a distribution? Flow balance equations to find the lambdas, and the mu's are just as they are. And they each look like, thank you, and they each look like an MM1Q. So like what is, let's answer a question here. What is the probability there is in equilibrium no one at server 2? So we want the marginal probability for server 2. You can get this by summing out N1 going from 0 to infinity and N3 going from 0 to infinity of that thing, that big thing. I'm using a notation, which is that the argument is telling me what this distribution is. So pi of N1 and pi of N2 are different distributions and should probably be written like this, but they never are, because the way I'm writing it, which is the way everyone writes it above, they look like the same distributions, but with different numbers plugged in. Looks like one function pi. I can easily sum out the N1 and the N2, because if you put a sum over N1 in front of this, then this does not involve N1, so it'll get pulled out front. This does not involve N1, so it'll get pulled out front. And we will be summing this as N1 goes from 0 to infinity, and that sums to 1. That's a nice little geometric sitting there. So if you did both of these sums, you're going to be left with only 1 minus lambda 2 over mu 2 times lambda 2 over mu 2 to the N2. And so we want the probability. Now this is confusing because I want to plug in a 0. And so what the heck is it? I'm going to write N2 evaluated at N2 equals 0. Because if I just say pi of 0, which pi is that? And this is 1 minus lambda 2 over mu 2. Yay! I said. Before I ask if that makes sense again, let's go back to the simpler example of the MM1Q with feedback, and then I'll ask you if it makes sense. Because that is a simplistic Jackson network. Go back to the MM1 with feedback. We've got a Poisson arrival process with some rate lambda. They line up and go into service with a single server with rate mu. And then with probability P, people come back and join the end of the line. So there's a line. And they will join the end of the line. Otherwise, with probability 1 minus P, they leave forever. This is a Jackson network. And we have one server. So it's a one server Jackson network. And we have to solve the flow balance equations. So lambda 1 is supposed to be the rate in and out of server 1 in equilibrium. And this is made up of an external stream with rate lambda, plus now the departure for the single server is also rate lambda. It's not rate mu, and I totally get why you would think that. It's only rate mu if there are a positive number of people there. But overall, if you average it out over the times when there are 0 people there, it's rate lambda. And so I'm going to thin out the, did I just say it? Yeah, I did. I am letting lambda 1 be the flow in and flow out. So I am going to have to send around P times lambda 1. So how do you get into server 1? You come from the outside, or you come from the output stream of server 1. It's lambda j equals the sum over I of lambda I Pij. And j could be 0. And P01 is 1 for this problem, because everyone that comes in goes to that server. Okay, so let's solve for lambda 1. Lambda 1 is going to be lambda over 1 minus p. And then Jackson's theorem says that pi of n1 is equal to a geometric looking thing with this as the arrival rate and mu1 as the there's no mu1, mu as the service rate. So we get 1 minus lambda 1 over mu to the n1. You don't need an n1. There's only an n here. I just wanted to make it look like Jackson's network. And this is 1 minus lambda over mu 1 minus p times lambda over mu 1 minus p to the n1. And this form kind of tells you how you might think about it. If we thought about the feedback as increasing the arrival rate, we just have to keep adding to that every time we go through. And we kind of had a little problem there. Instead of thinking of the feedback, this loop, as increasing the arrival rate, I would think of the people who don't get to leave, like slowing down the service rate. And so I've got like the arrival rate lambda and a slower service rate, a mu times 1 minus p. Let me make the flow balance equation just a little, I don't know if this is going to make it more clear or not. I'm going to not have the sum start from 0. I'm going to have an external arrival rate of lambda. Now this is supposed to be the arrival rate to server J. So then I'm going to have the probability you go from outside directly to J. And then the sum as I goes from 1 to M, that was our number of servers. The rate of leaving server I times the probability of going from I to J. This is exactly what I wrote before, but before I had I starting from 0. But maybe this is more clear. So you can really see the external arrivals and arrivals from coming back around. It's not at all. I was just trying to make it look exactly like Jackson's theorem. So I would definitely just call this N. Yeah, so going back to the, what is the probability there's no one at server 2 in equilibrium? What I did first is just try to get the marginal distribution for the number of people at server 2 by summing out all the people at server 1 and server 3. And then plugged in 0. And I wrote this in this strange way because what the heck is pi 0? Everything is being called pi. So I was like, this is defined by its argument to be the stationary distribution for the number of people at server 2. And then I plugged in 0. Okay. This is super fun, and I'm making it, I don't know. Let's do a break. Let's do a simulation break. Do, simulation break. Those are the only words to the song. Simulation break. Gibbs sampler. I have more Jackson networks to talk about, but yeah, let's take a simulation break because I don't know. None of that should have been, I hope that was okay for you. The Gibbs sampler. So you have a target, and just like with Metropolis Hastings, the target could be discrete, but it almost never is. So I'm going to think of it as actually it won't matter to the way I describe this, but it's likely a discrete target distribution. And for a Gibbs sampler, it has to be at least 2-dimensional. So I'm going to say like k-dimensional, where k is greater than or equal to 2. And so you need to be able to do something for every algorithm. Can you bound this? Can you draw from this? You need to be able to draw from the conditional distribution of each xi given the other x's. Usually in Gibbs sampling, people use a notation x, I'm going to do it lowercase because it's just going to be an argument of a PDF, x to the, with a subscript minus I to be x1 up to xi minus 1, and then xi plus 1 up to xk. So we need to be able to draw from the distribution of xi given x minus I is some value. Ooh, when can you do this? You can do this all the time if you're doing Bayesian statistics. But yeah, let me describe the algorithm and we'll prove that it works, and then we'll talk about an example. Okay, so here is the algorithm. I'm just gonna describe it with k equals 3. There's nothing that changes except I have more dots for general k. So you start at an arbitrary point. We're going to create a Markov chain. This is an MC-MC algorithm, Markov chain Monte Carlo, where we create a Markov chain whose stationary distribution is pi. So start at an arbitrary point and call this x1, x2, x3, and I'm going to give these like superscripts in parentheses so they don't look like powers, where the superscripts represent time. So this is time 0. And then when you are at time n, because I'm just going to describe this in a recursive way, time n at point x1 super n, x2 super n, x3 super n, here's how you proceed. Number 1, you draw an x1 from, and now I'm using this kind of notation again, where the arguments are describing the distribution. So I'm not going to put a name of a distribution, but the PDF, the conditional PDF for x1 given, let me back up. We're at time n, so I want to draw x1 at time n plus 1 from the conditional PDF for x1 given x2 at time n and x3 at time n. I don't know x2 and x3 at time n plus 1 yet. I only have them all at time n, so I'm going to update the first guy in there by drawing from the conditional distribution of that guy alone, given what I've already observed from the other 2 points. And then we're going to draw. So we're going to draw this from pi of the conditional distribution of x2. And I'm going to give what I know about the other 2. So I'm going to plug in x1 at time n plus 1 because I've already updated that. And x3 I haven't updated, so at time n. And then finally, I'm going to draw x3 at time n plus 1 using the conditional distribution of x3 given the other 2 x's, which have both been updated. There are many variations on the Gibbs sampler. You don't have to go in this order, and you can actually randomly select things, and you can do it in block form. Like if you have an x1 through an xk and you want to update x1 and x2 at the same time by drawing from a 2-dimensional distribution given the other k minus 2, like there's many different flavors of Gibbs sampler. And then you have a new point, and then you update from there. So let's see why this works. And you're able to do this far more often than you might think, especially if you are doing Bayesian statistics. Okay, let's prove it. Why does this give us the right stationary distribution? That this has the target, which I'm going to call pi x1, x2, x3 as the stationary distribution. The stationary equation for a continuous state space We've only seen this once, and that was with the Metropolis-Hastings algorithm. And our pi j equals the sum over I of pi I pij turned into pi of y equals the integral of pi of x p x y and running over all x. That was the continuous state space version. Yeah, you are correct, direct message. This only works if you know the conditional distributions. But this is the version of the stationary equation for continuous state space. Now for us, x, y, and z are three-dimensional. And I could just put vectors on them, but I want to look really specific here. So pi of y1, y2, y3. So this is like here in this particular case, we want this to be a triple integral. Like dx with a vector over it would mean you're integrating with respect to each of the components separately. So this needs to be pi of x1, x2, x3, and then a p taking us from x1, x2, x3 to y1, y2, y3, integrated with respect to x1, x2, and x3, and those integrals should be over the entire state space. So I want to show that this holds. And we were given a pi, but the Gibbs sampler algorithm is giving us a formula for the transition probabilities. The quote unquote probability, we go from x1, x2, x3. Now this is continuous, so this probability is going to be 0 if I say probability, to a point y1, y2, y3. How we do this, and this is heavily dependent on this idea that the argument of my PDFs are telling you which PDF I'm using. Like again, if you see an f of x given y versus an f of y given x, these are notations for really different functions. You know, that probably should have subscripts to say that they're not the same f, but it just gets way too messy too fast. So this transition happens in like 3 steps. First, you have to draw y1 from the distribution of x1 given the other x's. So I'm going to get a y1 from the conditional distribution for the first component given the other 2 components that I have at that point, times the distribution for y2 given the other, so that's y1, given the other 2 components, times the distribution for y3 given the other 2 components. So you see I'm updating. Here I'm given only x's. Here I have one of the y's that's already been updated. Here I have both of the y's updated. This is what the transition probability, quote unquote, it's a density, is like for the Gibbs sampler. So I'm going to go through the stationary equation, starting with the right-hand side. I'm going to put a pi x1, x2, x3, and then the p from x1, x2, x3 to y1, y2, y3, which we just worked out to be pi of y1 given x2, x3, pi of y2 given y1, x3, pi of y3, dx1, dx2, dx3. I probably should have spent more time setting up notation before starting this, because I did say we're using the arguments to describe the distribution. So like, for example, pi of x2 given x1 and x3 is supposed to be the conditional PDF for x2 given x1 and x3. It's supposed to be the 3-way PDF over the 2-way PDF. But now I'm plugging y's in. But the y's, I'm using the same, like this pi y2 given y1 and x3 is using this PDF for x2 given x1 and x3, but I've got it as a function of y2. Like there aren't different distributions for the y's. So in all, I have a target 3-dimensional distribution, and the subscripts on the arguments are keeping track of what's going on. How you guys doing out there? Let's do this integral. Wait, I've got results. That might be okay. If I want to do this integral, the way I have it written, my inner integral is with respect to x1, and check it out. I only have one thing with x1 in it. So I am going to speed this up here. For the inner integral with respect to x1, this is constant, and this is constant. So I'm going to pull those three things out of the x1 integral. I'm left with the three-way joint PDF for x1, x2, x3, and I've integrated out x1, which gives me, I'm down one integral, so I only have two left. And I have pi of y1 given x2, x3, pi of y2 given y1, x3, pi of y3 given y1, y2. Those all came out. And then the integral of this with respect to x1 over the entire space gives us the joint PDF for x2 and x3. And I'm left with the integral with respect to x2 and the integral with respect to x3. So in this step, I have integrated the three-way density with respect to x1, and that has given me the marginal PDF of x2 and x3. Does that make sense? I don't know what to make of that, but this times this, the first thing I circled there is a pi of y1, just write out the definition. It's a pi of y1, x2, x3 divided by a pi of x2, x3. And that is going to cancel with this one over here, that denominator. So I can rewrite this as the double integral of pi of y1, x2, x3, and then pi of, now I'm taking down this term, y2 given y1, x3, pi of y3 given y1, y2. I haven't integrated yet. All I've done is combine those two yellow circles, dx2, dx3. The next integral is with respect to x2, and the only place I have an x2 is right here. So both of these guys come out of the x2 integral. So I'm left with the integral of pi of y2 given y1 and x3, pi of y3 given y1 and y2, and the remaining integral of pi y1 x2 x3 with x2 integrated out gives me the, we go down to a marginal of y1 and x3, and then a dx3. So this integrated with respect to this gave me this. Actually, this guy could have come all the way out at the very beginning because there's no x's in there at all. I've got pi of y3 given y1 and y2. And what's left? I've got this conditional density times this density. And if you write out this conditional density, it's a three-way intersection divided by this one. That's going to be pi of y1, y2, x3. I get that from this and this. dx3. And if I integrate out x3, that'll give me the marginal pi y1, y2. So I get pi y3 given y1 and y2 times pi y1, y2. The first one being pi of y1, y2, y3 over pi y1, y2. and a pi, y1, y2. So we've got pi of y1, y2, y3, and that's what we wanted because we were trying to show this, and I started with the right-hand side. So I have a simulation coming up. It's going to be great. Please come back because I'm going to show you my three-dimensional histogram, and we're going to spin this around and look at all sorts of regions here in an example. And I will try to convince you that you know those conditional distributions more than you think you might. Next time on Markov processes.